and two-phase flow. So in reactor engineering, just to show some example, we work with the containment of a small modular reactor, coupled neutronics and small hydraulics of reactor, research reactor. So the next, the work with, this is a flow assurance that's mixed. I will talk it later. So Leidenfrost phenomena is rebating of hot surface above the saturation temperature. The printed circuit heat exchanger, in fact, this work was done for Petrobras. It's a Petrobras funded project for CFD simulation. But this reactor, this heat exchanger was widely used for advanced reactors. And finally, we have CFD and DEM, discrete element methods, coupled simulation of fluidized beds. Here is a fluidized bed is a nuclear reactor. So as soon as I joined U5J in 1998, I started to work with Professor Sijin and Professor Mulilo on several industrial projects for thermal insulation of and thermal analysis of subsea pipelines. Then we published a couple of papers in conference and journals. So recently, we have working with multi-layer pipeline with active heating. So Professor Anchen and me published work. Now we have another CSC visiting student, Yu Jinhong, working on the same topic for her PhD, and we got some very good result published at International Communication of Heat Mass Transfer. So Wang Hui is another student of Professor Duan and Professor Anchen. He came here also as a CSC visiting scholar. He got very good work published at Applied Thermal Engineering and Composite Structures. And this is also an SFC funded project. So the multi-layer pipeline with phase change materials, both lumped mass and with micro PCM particles. And parallelly, we collaborate with the Nuclear Engineering Institute of Brazilian Commission of Nuclear Energy to carry out numerical and experimental work on stratified gas flow, bubbly Taylor bubbles, and so these are some of our work on flow assurance. I think this book that authored by Professor Anchen, Professor Duan, Professor Sijin, and me best summarize the China-Brazil collaboration for the last decades. So this book was divided in three parts. The part one is structural analysis, mostly carried out by Professor Sijin and Professor Anchen. The second part is fluid structure interaction that I have presented work with Professor Anchen, Professor Duan, and the last part was flow assurance, the thermal analysis that some work we carried out together, Professor Sijin and me. So this, I think this book summarized our collaboration for the last decade. Now we are working for new books. So currently we are undertaking NP research project, also with funding from INPLAP, to develop a simulator for riser, convening multi-phase flow and has a fluid structure interaction. So the project is divided into 4 parts. One part is riser dynamics, is some some sort like Ocaflex. And we have also multi-phase flow part is also like auger, something like that. And then we have fluid structure interaction, both with external flow interaction like VIV and the movement of the floating platform. And with the internal flow, like we carried out for straight small deflection pipelines. So this, and then all these are integrated in a graphical user interface. So this project is ongoing. So we have some result. So the VIV result was already reported in conference, and now we also have a simulation of the top tension riser, and go ahead. We have a small diffraction riser. We have a large deformation riser, catenary risers, and steel level width risers, all simulated. Now we are working on the graphical interface and on the validation. For the multi-flow part, we are working on two models. One is the two-fluid model, similar to the auger, and the other is a slug tracking model, and it's also extension of our previous unit slug model. So both models are being developed separately, and later they will be integrated into the fluid structure interaction. So we have a flow map implemented, and we have a validation of pressure drop. We have a unified pressure drop model for all inclinations, for all flow regime, and now we are simulating severe slug. Also, we are, since February this year, we start a new project we call, with Petrobras, we call the Subsea 2X. So it's a collaboration with Gelo, Professor Seijin and Professor Milagi, with Lafay, Professor Hobson, Diaz, and Watanabe. Lancer is a laboratory in nuclear physics, reactor physics, with Professor Aquilino and Professor Alessandro. So this work are supported by Petrobras. So it's the objective is provide offshore power generation and electrification for offshore production, mostly for subsea production. So there is the renewable part by Professor Seijin and Milagi. Also, I forget, also we have a Lance, Professor Landau and Professor Luis Paulo. So this very extensive project has the renewable energy, ocean energy, offshore wind energy, OTEC, and the nuclear solution is floating nuclear power plant and a subsea power station. So that is our solution currently we work on. One is one is a floating nuclear power plant, FNPP. It is a recognized abbreviation, and a subsea nuclear power station. So both are underway for analysis and for the typical scenario application of offshore development in Brazil. Finally, our students take part in a BRICS competition. So their project is offshore hydrogen generation for low carbon technology. So the proposal is generate electricity by SMR, a floating power plant, and that provide electricity to offshore platform. If there is excess of electricity, it will produce offshore hydrogen. So it both can be electrolyzer of seawater or reformation of natural gas, and we have also other alternatives for transportation, to mix transportation with natural gas or heat generation with hydrogen. So this is currently another project that we are working on. So that is our conception of the future offshore production. We have a offshore oil production platform, a floating nuclear power plant, and offshore hydrogen plant, and that are our vision for the future offshore technology. Okay, so that's the end of my presentation. Thank you very much. So our lab is focused in multi-physics modeling and simulation. So simulation for us means simulator. So the lab was created to develop a simulator for nuclear reactor powered submarine, and we are still working on that our original part, and now we are developing simulators for offshore technology. Thank you.
Thank you, Professor Su Jian. Next speaker, Professor Jean David. Sorry, Professor Murilo. Sorry, Jean.
Hello, good morning, everyone. It's a great pleasure to be here again to meet some of my Chinese friends. So I will present quickly the recent activities we have been developing in our lab. I think most of you had a chance to visit yesterday. Can you go on, please? Sorry, I can manage myself here. Let me see how. Yeah. Okay, thank you. So the summary of my presentation, I will present the lab and some of our recent projects. Two are connected to use of composite materials with carbon fiber to repair structural members offshore, ship panels and tubular members. And the other ones are connected to the pipeline and risers area. We are studying the behavior of mechanical line pipes during the relay simulation, and thermoplastic composite pipes. We are working on this topic, and we hope to start some projects soon. I need to show here. Okay, so the mission, we are located in the Science Park. Our mission is to develop tests and models for analysis of offshore structures. The main research areas are related to rising pipelines, cables, offshore structures in a general way, and ships and subsea equipment. We are about 40 students, and we have students in research, and we have about 5 to 6 Chinese students. We have some experimental facilities. We have a tower where we have a rig to test the top connection of flexible pipes in the left-hand side of the presentation slide. We have a multi-purpose rig that we can test several components, static and fatigue loads. And we have a material testing rig where we can test composite material, steel, etc. We have 3 other rigs in the lab, a small one in the left hand, on the top left, to test mainly umbilical cables. In the bottom of the presentation slide, we have a rig of very high capacity, 500 tons, where we can test a flexible pipe with the bend stiffener and simulate the top connection. And we have a flexible hyperbaric chamber where we mainly simulate the touchdown point and instability of the arm wires, of the tensile arm wires of flexible pipes, subject to external pressure and cyclic curvature. So I'll talk quickly about the repair of tubular members. This is a serious problem in aging structures where they are, due to poor maintenance, they suffer corrosion, not only on the tubular members, but on the joints as well. And there is a lack of procedure to how to safely repair those structures using composite materials. Traditionally, welding and cutting is employed for these activities, but it's time-consuming and dangerous offshore. So we are studying to replace the traditional method by using composite materials. So these are some examples of degraded structures that need attention. Of course, ultimately we need to repair the entire member, but we need to see in which conditions we can have a more effective repair methodology. And not only the tubular members can be damaged, but often the connection as well. So how to repair it, how to dimension the material and the thickness of the repair to restore the strength. So we have done a long experimental campaign, a numerical campaign. I'm sorry I cannot go into detail here. So we simulate the process that will be employed, and we not only do the experimental validation, but we do all the the numerical campaigns and experimental and correlate the test for. So we test intact, damage, and repair samples under different loading, bending, compression, combined loading, for different geometries, different size, different damage, and to validate design curves for repair. We do a full material characterization. We do a large campaign of mechanical tests. We test several solutions for different composite materials, different suppliers, and with that we can feed back the numerical model and correlate with the experimental result. Of course, we test as well the steel properties and feed all this information into the numerical models that we create using different elements, different mesh. We do, and we can validate the tests. This is an example of a bending moment versus, bending moment versus rotation, a pure bending test. The right-hand side, we have a bending compression test. We see that the damage in the red lines with the damage, the hold, the capacity reduced dramatically. But if we use some laminates, we can reestablish the capacity of the structure. So we are starting to do, Petrobras starting to do this repair offshore. They are planning to do the first repairs offshore. We are also trying to understand the long-term condition of the repair, study behavior of complex damage, go deeper into the joint integrity and repair, and connect to inspection strategies and monitoring. So in a similar way, we are studying repair of FPSO side and bottom panels. Again, the structures are aging, they suffer corrosion, and the thickness loss is measured periodically, and they cannot dock, so they have to do in situ repair, traditionally using steel as welding, and this is dangerous and time consuming. So we are working together with Petrobras and ABS to develop a repair methodology for this kind of structures. So we are studying several aspects of the mechanical of the repair, especially concerning the interaction of the composite and the steel. And so this is mainly the scope of the project. We are focused on side and bottom panels, and to develop procedures for design and application to restore the panel strength. And this is, we are working together with the classification society and testing 3 suppliers. So we characterize the material. We do small scale panel, scale 1 to 3.5, and we fabricate ship panels. We characterize the mechanical properties. We do numerical simulation. We do compression tests in a panel combined with lateral pressure. We do the model validation, and we are going to study as well the degradation in oil. And so we move to another project we are carrying on at the moment to simulate the relay installation of mechanical line pipes with adhesive. So we are interested to study the improvement of the mechanical condition of such a pipe, mechanical line pipe, when we use a glue between the carbon steel and the liner. So the idea is to avoid the formation of wrinkles, which the shell buckling during the relay installation. The liner main function is a very thin pipe, which main function is to be in contact with the CO2 and aggressive medium of the oil and avoid the corrosion. And the carbon steel provides the mechanical strength. So but the problem is when you install it and bend it cyclically, the liner may be exposed to compressive loads and form wrinkles. This project is sponsored this project is sponsored by Sinoc Brazil, and we have a number of students involved in these activities. So, as I mentioned, there is a higher concentration of H2S and CO2 in our oils, so we need to avoid corrosion. So one possibility is to use mechanical line pipe. We are studying as well the fabrication process, because the way you fabricate may eventually impact on the subsequent process, the formation of the wrinkle. So we have a number of models under development. I'm not going to go through the detail here, sorry about that. So this is a schematic of the hydroforming process, where we can simulate all stages of fabrication. And we are at the moment studying the simulation of the relay installation method for the combined mechanical line pipe. You can see what can happen. You can have a detachment between the liner and the outer pipe because the connection is not metallurgical, it's mechanical. And eventually, if not well designed, you can induce the formation of a shell buckling, the wrinkling, which is not accepted. And the use of glue may avoid this condition. So we are studying that, developing analytical, numerical models, and of course for the relay simulation, mainly numerical finite element models to study this problem. Next step, we are going to start an experimental campaign to validate our models, and we hope to do that, to start doing that in next year. Our last main project is concerned the behavior of thermoplastic composite pipes. It's basically a pipe with a thermoplastic material, a liner inside, and then you reinforce structurally with a composite material, typically carbon fiber for Brazilian deep waters, and you have an outer layer to protect and pack the structure. So so there is a big demand as well because our flexible pipes have suffered fatigue, and we are studying this condition for Santos Basin, and with some advantage compared to other solutions. So the main objective of the project is to develop a cross-section, an end-fitting solution, and develop numerical models, and for all the structural assessment of this pipe, and validating these models with our own experimental tests in the lab. And this project will also have the follow-up of the classification society. So to complete the campaign of the test, required test to qualify the pipe, we will need to develop a new bending fatigue test rig, not available in the university for this specific application, where we will be able to apply 4-point alternating test and a box for burst and bending the pipe. So that's basically the presentation. We are excited to further collaboration with China and our colleagues from Tsinghua. So thank you very much for the opportunity.
Thank you, Professor Murilo. I would like now to invite the next speaker, Professor Fasheng Wang. Case study of underwater explosion to submarine pipeline. Thank you.
Thank you. Okay, this is Fasheng Wang. It's a great honor for me to be here, especially yesterday when we first arrived here. This place is named the Science Park. After viewing the mechanism between the innovation mechanism, it's a kind of management on innovation. So Science Park is very close to universities. It's impressive. For example, the Technique FMC just next to us, the testing facility is there, and after the system integrated testing being accomplished and out for the offshore installation, I'm sure if there were any errors, issues happened, the engineers there will have friends nearby from universities who can help them immediately. And from the other side, university professors absolutely know exactly what engineers or industries needs. So greatly appreciate the contribution, not only academically, practically, and also from the management innovation for how to improve the innovation more efficiently for the world. So greatly appreciate and inspired me very much. Today I'm going to talk about a topic named the case study of underwater explosion to submarine pipeline. Is the work presented today has been conducted by my PhD student Li Sumang and me. Let's briefly introduce my biography. I got a PhD from Imperial College London in structural engineering, focusing on steel tube. And after that, I worked in JP Canning London, now is named the Wood Group Canning, on submarine pipeline. And since then, I became a submarine pipeline man. And I worked, so after the work in the UK, I moved back to China to work for COEC. It's named China Offshore Oil Engineering Company, which is a subsidiary of CNOOC. And after working there for 6 years, I moved to Tsinghua University, School of Civil Engineering, continually doing submarine structures, mainly on pipelines. I'm holding fellowship for ICE, which is the Institute of Civil Engineers in UK, and also the fellowship for IMAREST. For IMAREST, it's another institution of the UK. Also chartered engineer of Engineering Council UK and PMP, professional management personnel of Project Management Institute in the States. 4 parts. So firstly, I will introduce the background. I'm sure everybody here knows submarine pipeline plays a great role for offshore oil and gas development. Previously, we never thought an underwater explosion could be such a crucial or practical threat to our existing underwater pipeline networks. But after 2020, when Nord Stream pipeline been damaged, this threat can't be ignored anymore, or we have to pay much attention on it. As a pipeline man, when I first know this happened, there are 3 questions comes to my mind. 1, why or how could this happen? Secondly, how did this happen technically? And thirdly, how could we do to minimize or ease the damage or results? With these 3 questions, we try to investigate it with limited information published. This is the video. This is the investigation. Is a video by ROV on the damaged location after a few days of these events. It's online. It's from internet. Very interesting, because when we thought with a hit, with a punch, but an impact such as underwater explosion, it should be a dent inwards. But rather than we found it's outwards, it torn, it kind of breaks, and the failure mode becomes outward. It's very strange. It's different from what we thought. And also some concrete coating cracks. So let's have a look at what's going on those days. There are 2 explosions. So one, 2022, And September 26, 2 a.m., after a few hours, there is another explosion. A total 4 leakage points being found in Denmark, exclusive economy zone, and the Sweden ones. So 3 pipelines being found leaked. And so the question 1, how could this happen? Or what's the result of this accident? We all know Nord Stream is the longest submarine pipelines. The capacity of it for natural gas is about half amount of Germany annual natural gas consumption. About 50% could be 50% natural gas consumption requirement for Germany could be provided by this pipeline. But after 2020, it's gone. Just a few months later, I'm sure the German people got the highest bill, energy bill, in that winter. And the winter now, well, of course here is winter, but I'm sure in the north part of the earth, the winter is coming. So nobody knows how high will the bill will be in the coming winter. So it's a question 1. It's a huge impact, not only economically, but also politically. Also, when we studied this issue, we found quite interesting publications. Look at the picture on the left side. It's a picture from 2016, which was 6 years before the accident by Nord Stream operation team, published on a conference. It shows the location. The location is very interesting. It's almost the same area as this accident happened. Very interesting. Scoring, cost, free span. Why this happened? Why this consistent coincidence happened? With these curious questions, we try to carry out numerical simulation to investigate what's going on. It's question 2. Although there is limited information publicly, but we try to dig it out. We found, the diameter, what thickness, the design pressure, and the material, etc. information. We try to adapt it, and also we found the accident happened in the third part of the pipeline, where the design pressure is about 17, roughly, megapascal. The reason why I mentioned this, we found the internal pressure played a great role on the failure mode and on the question 2, how did this happen? So we adapted a simulation of seawater, natural gas, TNT charge by numerical simulations, and according to some reports, maybe the TNT weight is about 500 kilograms and maybe a meter away. We don't know, so we studied. And also we adapted the commonly used the material model for steel tube, seawater, concrete, and actual respectively. Also, we considered the influence of the concrete coating. As we all know, when we designed a submarine pipeline, single pipeline, we commonly ignore the effect of the concrete coating outside from the perspective of load-bearing capacity. But this contributed to the pipeline when it had a threat from underwater explosion outside. When it comes to the validation, it was very unfortunate. We couldn't find even one published experiments. We couldn't find any submarine pipeline on the underwater explosion experiment. So we found one manual, US Army technical manual, which can predict the pressure of submarine pipeline outside according to certain explosion nearby. And after our model being validated, properly, we trying to investigate the full range, to carry out a full range analysis to see what's going on. There are two animations here. The left, they are from the same model. The left one, it was the fluid field pressure, and the right one was pipeline structure deformation. And we can see what's the whole process. And this, okay. So you can see when the TNT explosion happens, pressure approaches the outer surface, and when it breaks out, it will tone the outside. Similar things happened from the perspective of solid part. So it's very interesting. We found the whole process consisted of 3 stages. So stage 1, when the explosion happened, it took about 10 milliseconds for the pressure, the shock wave loading from the TNT charge approaches the outer surface of the pipeline and then breaks. After that, between about 10 milliseconds to 30, 40, or 50 milliseconds, the high pressure inside began to leak out from the bricks. It's very much like a can with a Coke. When we punch it, it pours out. Similar things happened for this occasion. And in addition to that, after another 10 milliseconds, the persistent gas leakage continuously happened, but until a stable situation be formed, because we couldn't use about the pressure from 500 kilometers far away. It certainly has a distance. This will help us to decide what was the actual pressure then, because we know 20 or 30 or 40 meters of the pipeline be damaged. So this is how long, about 20, 30, 40 meters, this number relates to the actual pressure inside at that time. Again, from the from the structure side, for the first stage 1, until 10 milliseconds, the pipeline dense due to shock wave loading. As tier 2, when the pipeline breaks, the internal high pressure explosion, the second explosion, I would say. And in the third part, sorry, I'll try to hold it. Okay, the third part here, so structure stabilize after about 100 milliseconds. And for that case, the high internal pressure stabilize as well. Afterwards, we conducted a parametric study to see what was the minimum requirement of the TNT charge, what was the location we put the TNT charge on the top of the pipeline, the bottom of the pipeline, or each side. And also we could investigate the distance. It's 10 meters away, or it's near, or is just attached on the pipeline. We carried out many studies. Due to the limited time, we won't go into details, but after the parametric study being conducted, we could approach a general conclusion on certain parameters. And we found, internal pressure played great role on the failure mode. We found the TNT, as soon as it's up more than 200 or 300 kilograms, the pipeline would be damaged as soon as the distance less than 1 meter, something like that. Okay, question 3. How could we do to minimize the damage or the results? As Sajang mentioned yesterday, sandwich pipe could be an alternative solution, and we also do some research on this area. We proposed a concept of carbon steel, concrete, cement in between, and the stainless steel, carbon steel composite pipeline is also sandwiched pipeline. And we were awarded an American patent and Chinese patent, and we try to adopt this concept to offshore oil and gas industry. It's been quite welcome, but we are short of design code. So we have been trying to carry out a study from fundamental research to technical solution and eventually for coding system. In China, in Zhejiang province, for cities relatively close to the coast, where the typhoon would happen very often, so the electricity transmission tower are dealing with similar loading situation as a pipeline, the very large lateral loading scenario. So we try to adapt this one to submarine pipeline. We did many experiments on different key parameters like Holy ratio, impact, and long-term sustained loading by considering corrosion, etc. And also we considered the feasibilities of production and installation, because we all know for SLA, offshore, for pipe-in-pipe system, we need to put the outer tube forward longitudinally. Now, how could this happen when we deal with the new structures? So we try to study the feasibility of production and the installation. After these two issues be solved, we compared the loading bearing capacity, especially to impact loading for the two structures. It's also animation for two different structures under the same loading scenario. So left one is single pipe, the right one is the new structures. Look at it. As I mentioned before, it's been broken, and for the right one, the structure integrating has been maintained. It shows great results, and we published. I have corresponding publication on the marine structures. Also, the code. About 4 years ago, we published a technical specification for concrete field double skin steel tubular structures, mainly for electricity transmission tower. 2 years ago, as the editor-in-chief, we published the design manual for submarine pipeline structures adopting such new structure. And this year, we will publish another design code specifically for submarine pipeline adopting this code. For example, we have our design equation, how much of loading capacity being left after underwater explosion, and we adopted this equation into the code and many other similar results. Conclusion. So firstly, we established the simulation and being validated, and it explained why the failure mode was outwards for the Nord Stream case. And also, we found a huge influence by the internal pressure on the damage pattern and the key parameters. And we try to propose a new structures which it help in the future. That's all. Thank you very much for your attention. Thank you.
Thank you, Professor Wang. There's a question here.
Yeah, Professor, very nice presentation. Yeah, we have been working on a sandwich pipe since 2005, and in fact, we don't use concrete. We use a kind of fiber reinforced cement instead. Yeah, it's a very interesting work you did. My question is, have you detected any collapse propagation after this blast? I mean, how long the pipe have been affected for this blast? Have you analyzed this kind of problem?
Yes, very, very good questions. And we met this problem when we were on, when we were studying. It is quite a crucial question. Generally speaking, it's about 100 meters, something like that. It depends on the internal pressure. If the internal pressure is 0, the damage may be just the influence of the underwater explosion outside. But if, let's say, it's 20 megapascal inside, it could be about 20, 30 meters along the length of the pipeline. But if it's high, 40, 50, we could answer it by our simulation. So generally speaking, 100 meters.
And another question: how was the depth in that specific point of the blast?
You mean the barrier depth?
No, the depth of the pipeline.
The water depth.
Water depth.
75 or 80. We don't know exactly.
About
the
shallow water.
Shallow water.
Okay.
Yes.
Okay.
Mm-hmm.
Thank you.
Thank you. Okay, now for the next presentation, it's a pleasure to invite Professor Jean-David Capras. He is the academic director of the COPE. Thank you.
Thank you, Milan. Good morning, everyone. I am going to describe quickly today some of the activities that we are developing in our LabSen laboratory. This is a small laboratory of ocean engineering department of the university, belonging to COPE, of course. And we are developing exclusively numerical simulations in that laboratory applied to ocean engineering, naval engineering, offshore engineering, mainly. I decided to only focus on 2 topics. The first one is decarbonization of maritime activities. Why is this important for us today and for Brazil and for offshore industry? First reason is that Brazil depends really highly of exportation of goods, like iron ore, for instance, like meat also, like soybeans. Okay, so the new rules of reducing carbon dioxide emissions are affecting really much this industry. But also, of course, it's important for all the logistic that is around the production of oil and gas in Brazil. You know that you have FPSOs and you need to offload the FPSO with a logistic chain, shuttle tankers, for instance. The FPSOs also need to be helped by support vessels, and all that logistic chain is consuming fuels, and that fuels are creating emissions, and of course this is a big problem. So we are studying some solution and developing some solution to better understand what can be the impact of that new goals and how we can provide solution on our most important thing is a solution that are cost effective for the companies. As I was mentioning, we have new goals, and you probably, all of you know the IMO, the United Nations, how to say, the United Nations service that make the regulation of the transportation on the ocean. But also for Brazil, it's inside the national waters. So you see that the overall goal here in 2050 is to have what we call the net zero. So we are in a really challenging phase from today onwards to reduce the emission to almost nothing in 2050. There are already some rules implemented, energy efficiency index, technical index, and also operational index that are already implemented. We are speaking about carbon intensity index and energy efficiency index. And today in London at IMO, we have some policies that are discussed mainly using what we call market-based measures, carbon levies and solutions that are similar to that. So, and all of that solution are going to be applied also in national waters in Brazil. So they are going to be applied for shuttle tankers, for instance, for short sea shipping, for cabotage, and so on. So there is a potential really high impact for industry. So we decide to develop numerical models that can assess efficiency in reducing emissions and also costs. We have different type of costs, operational costs, what we call voyage costs, and capital costs, CapEx, OpEx, and voyage. And with that kind of models, we can simulate the efficiency of various options that we have on the table to reduce the emissions. For instance, solutions that are based on the main propeller of the, or optimization of the main propeller. We can use the shaft generators, we can use air lubrication on some vessels. We have some solutions with wind assistance. You maybe know the rotor flattener that Vale Brazilian company implemented in some of the ships. We have advanced coatings, carbon capture and storage, waste heat recovery, and finally also alternative fuels. That is one of the options that we have to reduce the emission to zero. For Brazil, for instance, biofuels is really important, ethanol, biodiesel. We are speaking about ammonia. We are speaking also about hydrogen, for instance. The problem is that the companies do not know what is the best combination of that solutions that are going to be more effective at the lower possible cost. Another point is that we have here a speed reduction, which is the solution that is normally the most efficient or the most easy for the company to implement. If you reduce the speed, you reduce the emission. The problem is that if you reduce the speed, you reduce your transport of goods for 1 year, and you need to buy more vessels. It raises your CapEx costs. So we develop a big simulation model that can assess all that factors and find what is the best combination of option for any type of ships. This solution is partially implemented in one of our current projects in partnership with many different companies. This is an online solution that we will release next year, providing solution for two types of clients: for ports, authorities, port terminals that want to track the emissions of the second scope, scope 2 of all the operation in ports, and also for ship owners that are making cabotage in Brazil, or the ship owners that are making offloading of oil and gas in Brazil, for instance. This is based on online data, AIS data mainly, so the data that are coming from transponders of on-board the ships. Another big project that we are that is ongoing. So this is, to be honest, several projects that are ongoing since 2018 is a model of simulation for not only Brazil but for the world, where we are assessing what can be the economical impacts of the policies that are under the on the table of the discussion at IMO in terms of reducing, for instance, the GDP of the countries, or affecting more some countries than others. As you can see on that graph, for Brazil, this line is the number of tons of exportation from Brazil to China. So the thickness of the line represents the quantity of exportation. So the distance is really high. It is the highest distance that you can see on the graph with that thickness. So this is we can see that here that Brazil is far away from the other transportation line, and so that new policies can affect so much the GDP of the country. Of course, we are also developing some models specific to one objectives, and here you have an example of a small model of artificial intelligence that can predict the propulsion of a ship based on meteorological condition and the condition of the engine at a certain moment of the operation. It is interesting to be able to predict anomalies during the operation of a ship. So you can predict overconsumption, for instance, and try to track down why and solve the problem during the operation of the ship, for instance. It could be a container vessel, but it could also be a crude carrier if you want. Here I just put some of our research papers about that topic. One of here, two of them are really on the first one, and the last one, which is a preprint on the comparison of the effect of greenhouse gas policies developed by the IMO. The other topic that I want to speak about is artificial intelligence applied to ocean engineering and offshore engineering. And in that case, we have more than a decade working on that topic. And we developed some solutions for the oil and gas industry, mainly on three main areas of application. The first one is on productivity of construction of platforms. Could be FPSOs or fixed platforms or other type of platforms. Another one is on failure and anomalies detection. And finally, the last one is corrosion detection and prediction. Just a short example, you can see here a model that we developed in the past to be able to predict what is the time and cost of production of blocks of ships and platforms. We use neural networks to do that and historical data of the shipyards. The idea is to base the model on real detailed design parameters. I mean, we use weight of plates, length of welding, position of welding, density, dimensions, and so on. And then we are able to assess what will be the production costs much accurately than it was done before. It's improved the scheduling of the production, and you are more efficient when you are scheduling better the work. Another topic that we are working on actually is the automatic detection of defects on X-ray of welding. This is important for Navy application and also for offshore application. If a student that is going to defend his thesis next months on that topic. So we are using deep learning algorithm to try to help people to detect some defects like this pore here in the well. Similarly, in anomaly detection, we have developed solutions for rotary machines, and we developed some solutions to detect failures and characterize the failures, categorize the failures on bearings of rotary machine. It could be, for instance, here the case of a shaft of propulsion of the propulsion system of a ship. It could be also a gas turbine on board a FPSO, for instance. Similarly, and it is a really hot topic in Brazil today, we developed recently, and we just published the thesis of one of our students, the problem of detecting failures of anchorage lines. So actually, in Brazil, there are occurrences of failures of that anchoring line that are not detected quickly, and you can have weeks before to detect that the anchoring line is failed. So the idea, it's extremely difficult to put sensor on that line. You can put it, but it stays there for some months, and then you have the failure of the detector, the sensor. So we develop a system where you measure the position of the ship, okay, and also all the movement of the ship, and with that indirect measurement, you are able to detect not only a failure, but now we are going farthest of that. We want to predict the tension depending of the time. So we have a model that predicts the tension and failure of the anchoring line of FPSOs for many different loading conditions and weather conditions. In connection with the topic of Professor Murillo on corrosion, we developed some solutions on corrosion prediction for FPSOs based on Petrobras database. The idea is, as Professor Murillo was mentioning, you cannot bring the FPSO to the shipyard. You should make the repair offshore. And it's extremely difficult to predict what will be the steel quantity and number of plates that you have to buy to replace there offshore. So our solution based on neural networks, once again, is able to predict at any time for a standardized FPSO what is the quantity or the probability to have to buy plates and substitute plates for all the tanks of FPSO. It's improved really well the planification, once again, the scheduling of that repairs. And the repair, unfortunately, is not efficient at all, because when you want to repair one tank, you have to empty all the other tanks around the tank, and you lose productivity of the FPSO, you know. And I guess that's one of the last. You have here another example of corrosion detection, but in that case, we are not predicting the thickness of the corrosion or the corrosion loss. We are predicting only we are detecting the corrosion in images. The idea is to use ROVs, relatively cheap ROVs, to make a campaign of images, and then we can detect and monitor the progression of the corrosion in complex offshore systems, such as this tour of PLSV. And the last one is on detecting events, subsea events in monitoring campaign. We have application using pictures of IUVs, as you can see here, and also we have application using pictures of ROVs. This is in the idea of to be able to improve algorithm on risk-based inspection, so detecting the frequency and classifying that failures in former reports of inspection from decades ago. We can probably improve the algorithm of risk-based inspection and reduce the cost of that inspection in the future. So that was my presentation, and we believe that decarbonization, digitalization, and artificial intelligence are some of the keystones that will transform maritime activities and offshore activities in Brazil, and this is why we are studying that topics.
Okay, thank you, Professor. Any quick question? No question? Okay, thank you. So I would like to invite the Professor Alessandro Jacu for the next presentation, actually the last presentation of the first block.
Thank you, my God. I'm going to show you, we work with a group in robotic. Hi, Professor. Nice to meet you again. In robotics, okay, and I'm going to show just 5 robots who have been developed here in COP with applications in oil and gas industry in general, okay. So we are working with, let me see here. Yeah, so this is the professor, our senior professor, Professor Liu Shu, that have developed the group. And here you see the main expertise of the group, okay? We are working with, sorry. Oops. How can I go back? Just a moment. I don't know how to do it back here. Oh, it's okay. Let me show you what's going on, then I come back to explain. This is a robot for top. Okay, you can go back, please. Thank you so much. That was, okay, now I can, so this is the professors, and this is the expertise of the group I'm talking about. This is we are working with robotic, we advanced the algorithm for control of robots, okay? In particular, a structure named with high gain controllers, and underwater robotics, offshore robotics, and mobile robots, okay? This is the main topics we have pursued in our group. Autonomous drones, autonomous mobile robots, submarine robots, and multi-robot systems. So that's why we're talking about robots from minus 1,000 meters to 1,000 meters, since we are working with underwater, in surface, and in the air, okay? So we have to show you 5 robots or 6 projects. The first one is the Doris. This is a robot developed for topside inspection. This is you put in the platform a rail, and the robot goes in the rail carrying a lot of sensors to make measurements in the platform. Okay, this is the main idea of this project. This is a project that has a prize in 2017. Now we are with a new project with quadrupeds. Okay. To replace this system in the platform, but it is also difficult to do that. So this is not an old system, this is an important system yet to send the rail and to send the robot in the rail to go along the pipes, okay? So you can see the move. Could you play, please? Thank you. And you can see that the robot's carrying. The idea is you go around in the platform, take the images with all in the place, and then in a second round, the robot detects some anomaly. Maybe anomaly in a device, or just an operator that has left a tool or a bag in the system. The novelty here was the tracking system that is able to put the system in a vertical position to make inspection. And the manipulator can touch something with a vibrator sensor, for instance, and make the measurements that we need. A lot of sensors carrying this mechanism. Okay. And this was developed with Statoil and Petrobras at the time. Could you? Could you pass for another? Yeah, this is a mobile robot that can climb the stairs. The idea is to carry a manipulator to make measurements of the role in a minor industry. As you can see here, they need to go in a very bad terrain to go to climb the stairs and downstairs, and carrying sensors to make measurements in the role of the minor carrier. Okay, that's the main idea for the Valley of the Rio Doce at the time. Here you can see the robot in the 68 platform. Could you please just touch the? Okay, go there. This is another project. The first one is the idea here is to detect oil spill in the sea. And the system is a radar looking ahead, 3 kilometers ahead in the sea, and a thermal camera that can check if the radar is see real oil spill or another kind of plants or anything in the field. So just, okay, no problem. Another one. Here's another project that now is a surface vehicle, okay, equipped with a drone. We have put in the drone some electronics to make it autonomous in the landing, or takeoff, and the trajectory tracking. And then we go back to the boat and to make the landing in autonomous way with the boat moving. Okay, that's what the more challenging part here. And we have developed this and tested this in the sea. Okay, this is the project with the main ideas. And so you have any problems also with the video? Can you go? Sorry for that, but yeah, it's. So you can solicitar acesso. This is an underwater robot. We have tested this in the ocean tank here in the copy. And it was developed for underwater inspection. And we have taken this robot to the Antarctic in 3 years consecutives. Okay, and this robot was developed for detect how can I say the underwater life, okay, and was tested also in Antarctica, but we don't have to show here. Okay, yeah, I'm sorry. So the next one, and this is another technology that I have developed with Shell now, is to additive manufacturing. We are working with, and we are constructing some piece. But the idea here is to make it in a closed loop, and so you can go from the CAD draw to the final piece with high quality in the topside platform. That's the idea of this project. So you have also problem with the video. Sorry for the videos. The idea was to show everything, but so that's the main idea I got to show you. Any questions?
Thank you for your presentation. In the presentation, we have seen that you have been using the UAV, the unmanned aerial vehicle landing in a moving boat.
Yeah.
So it's hard to control this process. So I want to know if you have any experience for the UAV using inside the space, let's say inside of a building or inside of a tunnel or inside of a boat or some scenarios like that.
Inside of a boat?
Inside in the inner space of something.
Yeah, you have the drone to land in the moving platform. That's the
To
question.
control the movement of the UAV inside of something.
No. We're not controlling the move of the UAV.
Okay.
We're just controlling the drone. That's the question?
Yeah. I just want to know about the control of the UAV.
No. The idea is develop a robust enough algorithm to be capable of landing in a moving platform with the vehicle also moving.
Okay.
So you don't have information from the vehicle. You just do that with vision and with RTK GPS position.
Okay.
With high precision. That's the question? I'm sure.
Okay.
Okay.
Thank you.
I think that was the question, I think.
Yeah?
Yeah.
I think so.
Other questions?
A pena que os vídeos não passaram.
No questions? Okay, thank you.
Okay, thank you. Sorry again pelos vídeos.
Okay, we're gonna have a coffee break, 15 minutes of coffee break, then we go back for the next block. Okay, let's start the second block. The first presentation, the first speaker is Professor Ron Liao. The presentation is about the marine particle in situ classification bubble detection. Thank you, Professor.
Hello, everyone. It's my first time to be here, and I crossed the planet to come here. So it's a historical moment for me. And yesterday, I visited 3 labs and centers. And Professor Milay, Professor Murillo introduced us about their labs. So at the first, I'm glad to share 2 points with you, everyone. The first is I was most impressed by the very close collaboration between the university and the company. So it inspired me much. Is the first point. And the second point is Professor Xijin and Professor Duan have built the tight relationship between Brazil and China. So at this historical moment, so it's for me and for the young students, so we should push the collaboration further and deeper. So these 2 points I want to share with you. So it's much more for me. So let's begin. And today I will introduce you about my work. The title is about in situ classification of marine particles. I have worked in this direction for 15 years. So, and mostly in recent 5 years, we have published more than 50 papers in this direction. So that's what I will show you. I will share with you the recent progress in this direction first. And the second, I will show you about the bubble detection. Is new for me, but our method is powerful and effective. So I'll show you. And then finally, I will. Oh, here. Yeah. Finally, I will give some future plan in my mind. Just the plan. And okay. First about the in situ classification of marine particles. As we all know, particles in water is very common. Very common. And there are a lot of different categories of particles. Generally, the first is microalgae. Microalgae provide the oxygen and the primary production in the marine ecosystem. So it's very important. It provides food for the fish, for some other animals or any phytoplankton, zooplankton in the seawater. So it's very important about the microalgae. And also, they are related to the marine carbon. Is related to the carbon to the global warming. So it's So they are very important in marine microalgae here. And also they have some harmful algae in seawater. So if we so in the monitoring of environmental pollution, we have to detect or probe the category of the microalgae and count their numbers. Because if the number increases very speed, this microalgae do harm to our ecosystem. So this is the point. And the second one is about the second particles in seawater is microplastics. Now there is new pollution in seawater. So and I think everyone know this. And the third one is the sediment, sediments in seawater. So here is this slide. I want to show the important role of particles in the ocean processes, including the physical process and the chemical, biological, ecological, everything. So marine particles just take part in almost every ocean process. So it's very important to find the category. Category is the type, the kind of everything. Category of the particle and the number of the particles. So these two requirements. And here they have a lot of method to detect the particles in seawater. Here, a lot of. But if we want to know the category of the particle, so we here imaging and the single measurement are selected mostly here. And my research is about the single measurement because the imaging is time consuming. Because you take a photo to take a picture and count the number, so it's time consuming. And this one about the single measurement, we always use the optical scattering. It can work very efficiently. For 1 second, always can detect the particles about 100 or more. So it's very efficient here. So, and comparing our method, we use the polarized light scattering, and I will show you later. And we just use the single particle measurement method. So we this category. And the measurement is based on the polarized optics here. Here is the light source here, and the source illuminate the sample, the suspension, many particles in water, and then the particles will scatter the light everywhere, every direction, and one can measure the scattered light here. So we just know the incident light here is described by Stokes vector. It's just about optics. Yeah, we use Stokes vector to describe the polarization of light. Here is the input. Input is output. So by comparing the output with the input, so when we get the information about the particles. So we just use this very simple formula to describe this physical process. So here, this is the input, this is the output. This 4+4 matrix is named as Mueller matrix. It describes the polarization properties of the particle. So we just measure this output of light, or we measure the Mueller matrix, then we can get the information of the particle. So this very simple is all the physics here, all the physics here of the optical polarization technique here. And my innovation in my work is we combine polarized optics with the single particle measurement together, and we found that is very powerful here. So we develop a different kind of prototypes. Here is all the prototypes I built here. And also, because I have worked in this direction for 15 years, so we have developed a different kind of method based on polarized optics. Here, this polarized optics is the other method, combination. Is just the developer the prototypes to serve different kind of applications. So here, and I give you 2 examples. The first example is we just measure the scattered Stokes vector, and it carries the information of the particle. Is very useful. We can use the Stokes vector to discriminate different kinds of particles, including microalgae sediment and microplastics. And the second example is we measure the Mueller matrix here, and we can find that we can classify a lot of microalgae, and we propose a concept of polarization fingerprint. Everyone has a fingerprint, so we built the polarization fingerprint for each kind of microalgae here. So it's example here. So this data can classify the microalgae very accurately with very high accuracy here. And another is about the classification of microplastics. It's a very hot topic. Plastic. So we can see that if you just use the image method, these two different kind of microplastics, so it's hard to discriminate them two because just the shape, size, similar. But if we use our method, so the accuracy is very high. We almost can regularize each kind of them very in very high accuracy. So here, and we also studied the physical mechanism. And finally, we found that the origin of the polarization difference just arranged from the refractive index difference. And here, and I will show you very quickly about the prototypes. Here is 3 kind of prototypes. Here is in situ prototype. It can work underwater, and this one can work in lab or on ship here. And this is just a microscope, a special microscope. So we have developed all the prototypes with the module, standard, small, and smart here. And here I will show you the deployment of my in situ prototypes here. Please help me to show this video. Okay, here is a video. And maybe, okay. And the key function of the prototypes is just to classify particles in seawater, okay. Here we also deployed our prototypes in deep sea. Here is the deep sea. Is the most deep is 4,000 meters. And also we use multimodality measurement here. It is the prototype here. And we measure the polarization signals and measure the fluorescence signals together at the same time. So we can use this accumulation of the two signals together. We can classify the particles efficiently. Here is one example for the example. We just apply this method to judge the cells after the drug treatment. Here, we just bring some drug to the suspension, and then we use our machine to measure the cells in this suspension, and we can judge the cells is died or alive. Here, example. And this one we use this machine, this instrument, okay, in the field, and we can just recognize the harmful algae in water, in fresh water here. And about the bubble, here I built a camera, polarization camera here. Here's the light. Here is the light source. Here is the camera. There is a special to generate the bubbles here, and I will show you the result. Here is we can recognize and count the bubbles here. Here is very good, and you can see this. This is raw data. Raw data. If you can use the camera. Every camera, you can get this result here. But if you use our camera, you get this. These two. These two. So very effective. And if we use this camera in the very turbid water, the turbidity is about 72 NTU. So here, you cannot see, the color is dark. You cannot see the camera anyway. So you can see that the raw data is here. But if you use our camera, you can see. Here, you can see the bubble very clearly. So, 1 minute? Okay, good. And the requirement in ocean engineering here. There is some leakage of gas or oil in ocean engineering, in the underwater oil factory here. So they should have a video. Please help me to play the video. Okay, no problem. You can see that in the leakage here, oil here. And we have developed a method to detect the particles in water very efficiently here. And we can detect 8,000 particles in 1 second here, and classify the category of the particles effectively. And in 20 and 22, and my plan or project is expected here. In-time detection of gas and oil leakage and positioning in deeper water here. We just combine the profile detection of the particles and the fluorescence. So we just can classify the different kind of particles by the polarized optics, and we recognize the oil droplets by fluorescence here, combine them together. Okay, so finally we can detect the bubbles and detect the gas and the oil leakage in deeper water. So all is my report. Here is my contact information, and every collaboration is welcome. Thank you.
Thank you, Professor Liao, for the really interesting presentation. One question here.
Hello, Professor. Very nice presentation. I have a question. In fact, there is a huge discussion about microplastics and plastics in a whole. How have you did some field tests about these microplastics and how it could be done?
Our underwater prototype has been deployed in different areas in coast, China coast, and we can just detect or clarify the microplastics in seawater, but the proportion of microplastics in seawater in Chinese coast is quite low. It's below 5%. All the particles, all the particular matters. The number proportion is less than 5% microplastic.
In relation to all the particles?
Yeah, all the particles, everything, the micro algae or sediment, everything. So is the concentration in seawater, in coastal seawater, so is very low. But they are very harmful to the health of the sea for human beings. So I believe, I don't know everything about this, but I believe that we just the only team to in situ detect the microplastic in water.
Okay, thank you.
So the other people just bring the water sample to the lab and use the microscope to see the microplastic. So we can work in situ. Okay.
Talk later. Thank you.
Thank you, Professor. For the next presentation, I invite Professor Fernando Souza, Laboratory of Structural Analysis and Reliability.
Thank you, Milad. Good morning, everyone. It's great to be here today to make you this presentation about our activities at LaSalle. LaSalle is one of the labs at COPI. It means Laboratory of Analysis and Reliability of Offshore Structures. And we are linked to the civil engineering program at COPI. Civil engineering program has some research, some concentration areas. So linked to the oil and gas area. Having some trouble to align this microphone here. We are a group basically today composed by 4 professors, 3 senior researchers, some postdoc researchers too, and several students, including doctorate students, masters, and also undergraduates. We have lots of undergraduates, So it's one of the policies of the lab is to contribute to the formation of the future engineers. And we have also some TI technicians and technicians to help us. Our lab is the senior researchers of our lab started working together about 1987. So we have some more than 30 years of experience helping our partners in the development of methodologies, computer programs, applications to help the development of the oil industry here in Brazil. Our research areas, most of them are directly linked to the numerical modeling applied to the structural analysis and the design of offshore structures. During this almost 35 years, most of our time has been dedicated to basically to risers. We were helped mainly Petrobras to develop some methodologies, some technical specifications, some computer programs to allow the evaluation of dynamic analysis of rigid risers and flexible risers, and also some mooring lines. For instance, our lab was one of the developers of the software that Petrobras uses for global analysis of both rigid risers and flexible risers, which is the computer program Flex. Don't know if anyone here heard of it. It's similar to OrcaFlex, like that. We also were helped in the development of POSFAL, which is the program they use to compute the fatigue analysis of rigid risers. We are the developers of the software that they use to perform fatigue analysis of flexible pipes. And also we have worked very hard on VIV and VIM analysis also for these partners. More recently, we have some the developments of several applications related to structural reliability. It seems that the structural reliability is very on top today. It's a hot research line today, and we are applying these concepts of reliability to the analysis of risers, mooring lines, and also wellhead structures. We also at the lab we have a very strong research line related to the advanced finite element modeling of flexible pipes. We have also in the last years worked very hard on torpedo piles for Petrobras. We have several papers published in international congresses like the OMEI conference about these torpedo piles. And we have helped also Petrobras in the development of these underwater buoy supporting risers structure some, like I think 10 years ago, that they are using in Tupi field. We helped them in the development of the riser analysis and also in the design of the underwater buoy structure itself. It's a huge buoy, submerged buoy, that they use as a structure, support structure for the risers at Tupi field. And we also have something about offshore wind turbines. Our most important partner is, of course, the Petrobras Research and Development Center. It's located here close to the university. It's a walking distance. So most of our projects are related to the Petrobras Research and Development Center. But we had some years ago some projects also with Petrobras America between 2009 and 2012, I think. We had some also some projects with Transpetro because it was a design of some buoys they use in their operation. And more recently, other partners in the industry began to look for us for solutions. So this MFX is a industry located in Salvador that produces umbilicals for Petrobras and other operators. Shell, we have some projects also with them regarding some ships. ABS as well. Delp is a firm that designs the torpedo piles. And also we have some partnerships with other universities, such as the University of São Paulo. The project of the submerged buoy was conducted in partnerships with them. And also for more recently, other labs at the universities, such as the structures lab, that is helping us in a project being conducted right now. Just to illustrate a little bit better some of these application areas, I will talk very briefly about two projects that I think some projects that we are developing right now, and then I will talk about two projects that I am participating, and I think they illustrate quite well the capabilities of our lab. These recent projects are the flexible pipes life extension and integrity management. This is a huge research line. They are very interested today, the Petrobras Research and Development Center, because they have several hyzers that are operating for a long time, and they want to know if it's possible to keep working, to keep using these hyzers in the oil production, or if they need to be replaced. So the integrity management of these very old hyzers is something that is making them very, very worried, and I think we are helping them in these solutions. Also, with Petrobras Research and Development Center, we have we are developing a methodology based on reliability for the design of mooring systems. Something that is a very hot topic today is the stress corrosion cracking problem. This is being a research being conducted by a small group inside our lab, also in partnership with the Petrobras Research and Development Center. The well cement sheath reliability analysis is something I will talk a little bit more later. We are helping them to apply structural reliability to the design of these cement sheaths. The sandwich steel concrete FPSO hull is a project being with Shell and ABS. So the idea is to develop it, to study this kind of solution. And also, this is a very long project, the torpedo anchors design with Delp Engenharia and also with Petrobras. So the projects that I want to talk to you a little bit more are two projects that we wrote papers about it and presented at the OMA conference at Singapore this year. And they kind of illustrate quite well what we do in our lab. The first is the hyzer fatigue digital twin. Since 2004, we have been working very hard on the development of methodologies to evaluate fatigue for flexible pipes. So we started developing a methodology which is condensed in a software called FADFlex. And this program is a great solution because it allows the evaluation of fatigue considering a huge number of sea states. This was not something very usual when we started to develop this code. The fatigue evaluation of flexible pipes was a very complex task, and it was very hard to use several C-states to evaluate this fatigue life. So we developed a methodology that could help us doing this. But this analysis was still very time-consuming. A complete fatigue analysis of a flexible hyzer on the time domain is something that you perform it during a whole week. So the computational cost was very, very hard. Then we developed a very analytical or simplified numerical solution in a new methodology that generates conservative results in terms of fatigue lives in a very, very short time, in a very, very short period of time. The idea is to use this very conservative methodology to perform the analysis very quickly and use these results to evaluate the need of performing more expensive analysis. As soon as we developed this methodology, they asked us to help them, the Petrobras Research and Development Center, asked us to help them to develop a new methodology to manage the fatigue life of their hyzers that uses the raw movements at the platforms, or its data measured at the platform, and also internal pressure information that they have in a database to allow the evaluation of the flexible pipes lives, eliminating uncertainties related to the motions of the platform. So traditional analysis uses the RAOs and C-states to evaluate top motions, but this methodology here, which is implemented in the hyzer fatigue digital twin, it uses the raw motions at. How can I come back? How can I come back here? Milad, how can I come back here? De baixo. Andando para frente sempre. Come back several slides, please. Yes. Com ele tem que ser em português. So this methodology uses the motions measured at the platform and information about internal pressure at the hyzer at the platform, instead of using design considerations for this. So this measured data, it's collected by the data collector service, and these top motions, they need to be processed because sometimes the sensors generate spurious data, signals with mean values different from 0. So we have to make some processing on the signals before use them to evaluate the fatigue life. Then we have this analysis service that is based on our simplified and conservative methodology. And finally, these results are presented to the users in a dashboard where they can evaluate several aspects of the fatigue life of several hyzers. The idea that Petrobras told us they have is to use this simplified methodology to evaluate fatigue lives for all hyzers they have installed at Campos Basin and Santos Basin here in Brazil. And the results this kind of application gets is basically to evaluate these top motions, so we can compare the long-term statistics of motions really measured at the platform with values that we use at projects, the design criteria that we use in the projects to determine if our previous considerations were too conservative or not. And also, we have the results of the fatigue lives, which are the most interesting results in this case. And by considering only the few results we have today, it seems that we can increase the fatigue life of these risers when we consider these real motions at the top of the platform, and also the pressures measured at field. It also seems that we need a relatively long time series of data to consider that the fatigue life is reaching a stable value. Here we have in this graph here we have a 4 years span of time. It seems that about in this case here, it seems that in just 1 year, 1 year and a half, it seems to be stabilizing the life, but we have some other results where the fatigue life stabilizes after 3 or 4 years. So we need some long data series to evaluate these fatigue lives effectively. And the second project is a project that applies reliability concepts to the design of the cement shifts in offshore wells. When they design these casings and cement shifts to be used in offshore oil wells, they have to test these structures to evaluate the process of cementation. So they do this considering some properties for the cement, for the casing, and for the formation that are basically deterministic properties. And they evaluated the remaining capacity of the cement shift based on these deterministic properties. What we are doing for them today is to evaluate statistically these properties and to calculate the failure probability. 1 minute. And to evaluate these failure probabilities considering these statistics. So in this project, our scope is to evaluate the distributions of some specific properties of the cement shift, which we do basically in partnership with the structures laboratory at COPI, and apply the first order reliability methods to get to these failure probabilities. We started to get results recently, and it seems that failure probabilities for the examples that we analyzed are very consistent with the criteria that they use today to evaluate the remaining capacity of these structures, which is always good news. And this procedure also gives some information about importance factors, which help us to identify these variables that we need to treat statistically, and the ones that we can treat deterministically. So thank you very much. I think I'm just on time.
Thank you, Professor Fernando. Any question? Professor, one question, please.
I have one question, because you mentioned that you use the DQ2 method to predict the remaining fatigue life of a riser. So my question is, because I saw that you use a S-turn curve, I believe you also calculated the mechanic properties like bending, tension, and torsion maybe. And I think you use the motion of the FPSO as the input. Okay, so my question is, so what is the location is your reference, the position to analyze the fatigue life? Because if your target is a touchdown zoom, because we understand that the touchdown zoom, the response is actually not quite relevant to the motion of the FPSO. If you use a motions FPSO as the input, but how can you get the response of touchdown zoom of the riser?
By now we concentrate our the fatigue life determination at the top region of the riser. We are more worried about connectors and bend stiffeners.
Okay.
TDZ is something to be studied in the future.
All right.
So what they do is they collected the top motions, the motions of the platform in sensors that we know the location, and we transfer these motions to the top of the riser that we want to analyze. So this is we can calculate the motions at the top, the riser top connection.
Of course.
Then we have this simplified and conservative methodology that allows us to evaluate the fatigue life. It's analytical or sometimes simplified numerical procedure. We understand that the values that we are calculating are conservative. So if the fatigue life is according to what we want, there is no need to perform more detailed analysis. But if you find some problems, and if the riser is a relevant riser, we can perform the analysis on the time domain using simulations in our flex and FAD flex, and then evaluate the real fatigue life of the riser using the stop motions.
Just use the top motion.
Yes, just use the top motions by now. There is no this project is being developed right now. We're starting to get results, but we understand that we need to take into account more factors in the future to allow a better evaluation of this. So we have to improve our methodology a little bit, but it depends on what information we have also from Petrobras.
Yeah, because I also did something about this. So my experience is only the motion of the floater is not enough. If possible, because we have for example, this is a lazy wave, and if you have the motion of the buoyancy net section, if we can add a sensor there to get the motion of that lazy wave, that buoyancy, that section, and then it's better that we can get the better result, the response of the touchdown zoom.
But for the top region, this is not so important, because our model simplified model takes into account the existence of the buoys. So for the top region, this simplified methodology gives the dynamic response of the riser, taking into account the buoy. What we cannot do today is to evaluate the fatigue life at the buoy, because in this case we would need better information about the buoys, and so the sensors would be really necessary. But for the top region, we are quite happy with the results we are obtaining.
Okay. Good to know. Thank you very much.
Thank you for your question.
Thank you.
Okay, thank you, Professor Fernando. For the next presentation, I would like to invite Professor Yutao Gu.
All right. Hello, everybody. Good morning. I'm Yutago. I have given my presentation yesterday afternoon. Now, I will give this presentation on behalf of my colleague, Professor Ouyang. And first of all, I would like to start by expressing my apologies on behalf of Professor Ouyang, who is unable to be here today because he was previously giving a speech presentation in Singapore, and he should be right now on the airplane fly here, which is a long trip. So I will be speaking in his place. And before I begin, I would like to have a brief introduction to Professor Ouyang. So this is him. And he's a young and outstanding scientist and has made significant contributions in the fields of geotechnics testing equipment and in situ testing. And his research results have been widely applied in the geotechnic industry, and he just won the Bright Spark Lecture Award from the International Society of Soil Mechanics and Geotechnical Engineering. And the abbreviation of this association is ISSMGE. And today, we would like to share with you the application of new technologies and equipment in deep sea resource development. I will talk about the subsea drilling rig and its development history. And we will also discuss its potential application in deep sea and mining in the future. Let's get started today's presentation. As we all know, Brazil is a country with non-coastline, which means it has abundant deep sea oil reserves and various deep sea mineral resources such as nodules and hydrothermal sulfide deposits, just like other maritime nations. Given that the increasing depletion of land resources, people on Earth start to develop marine resources. But now, can we know and how get the deep sea material resource across several kilometers of seawater? It's hard to not that quick. So our current experiences tell us that the way to solving this task is utilizing geophysical means combined with ocean drilling technology. Geophysical methods are mainly used for preliminary delineation of subsea mineral resources, while drilling aims at the precise assessment of the resource quantities. And however, ocean drilling requires a drilling vessel and other auxiliary equipment, which is quite expensive. So how to explore and develop marine resource more economically and efficiently has become a hotspot for scientists and engineers in many countries. Seafloor drilling rig may be a permission substitution. Here is the subsea drilling rig image. Typically, it consists of components such as drilling head, rotating trunk, loading arm, magazines, feeding system, drilling string, and casting trunk, which I would say this giant machine may be the best way to improve the efficiency of offshore drilling. You may figure it out after the comparison between them. Conventional offshore surface drilling requires a scientific drilling ship for drilling platform as the base, and the drilling rig is mounted on the ship. To get across the sea water, we usually need hundreds of drill pipes and castings, which means a high capacity requirement on the rig. And such high levels of pipe handling and long periods of time to run and pull the drill pipe to reach the sea bottom actually is not always available due to the weather conditions. By contrast, seafloor drilling techniques put the drill rig on the seabed directly as the rigs get power and commands from the ships through a umbilical cable. This working mode would improve levels of operational efficiency and flexibility and decrease the risk caused by the weather conditions compared with the vessel-mounted drilling system in deep water, which results in significant cost savings. Since 1960s, Scientists and engineers have been building seafloor drilling rigs, which can be divided into 4 generations to this day. The representatives of the first generation of seafloor drilling rigs are the 3-meter drilling rig of the University of Washington and 1-meter drilling rig of Changsha Institute of Mining Research in China. The 3-meter drilling rig has a core diameter of 36.5 millimeters and can only be leveled within a 15-degree slope. The drill was successfully deployed in 2,400 meters of water on the Zhuangdoufaga Ridge during August 1990. The drill can penetrate and assemble 3 meters of vertically oriented core from crystalline igneous rocks, leach fields, sediments, and subfields and carbonate deposits. It is deployable to a depth of 5,000 meters, limited by the cable and drill weight by conventional research vessels using the NSF standard armored conducting cable. But in 1991, the instrument was lost on the cruise when the dynamic positioning system on the RV malfunctioned. The 1-meter drilling rig from Changsha Mining Institute has a relatively large core diameter of 60 millimeters and slope adjustment of 20 degrees, and it was successfully deployed in South China Sea in 2003. Obviously, the characteristics of these rigs are shallow drilling depths and monofunctional. By the end of 20th century, significant improvements were made to subsea drilling techniques. For instance, BMS was developed by Wallinson and Associates for Japan's Metal Mining Agency. The abbreviation is MMAJ, and successfully tested in 1996. The drill had a depth capability of 30 meters and 12 kilometers umbilical cable. Its core diameter is 48 millimeters, but it is permanently installed on the MMAJ research vessel Harry Malu number 2 and is not offered to scientists outside of Japan. Another similar drilling system, the portable remotely operated drill, PROD, the second one, also partly constructed and designed by Williamson and Associates, has a coring diameter of 40 millimeters and can potentially drill up to depths of 100 meters, but it is limited to water depths of up to 2,000 meters due to cable strength considerations. In comparison, although the updated drill from Changsha Mining Institute has a drilling depth of only 20 meters, its operating depth can reach 4,000 meters, and the core diameter is 55 millimeters, which is larger than the core diameter of aforementioned drilling machines. The second generation subsea drills are characterized by significant improvements in drilling depths compared to other predecessors due to advancements in automatic connection technology for drill rods as well as wireline coring techniques. When the first drill pipe is drilled in and the core was retrieved, the robotic arms on the rig will take out the second drill pipe from the trunk and connect to it in the first one. Meanwhile, the coring tool will be loaded into the drilling string and drilling procedure will be started. After it is finished, the coring tool will be retrieved by the wireline system. The robotic arms will hold and put it to the tool carousel. By repeating the above process, we don't need to pour up all the drill string in the strata, and coring is achieved, which help reducing costs and saving time a lot. As shown in the left picture, there are some more developed coring tools, and on the right is a photo of the wire rope coring process. As we can see from this photo, the wireline coring technology requires precise coordination among all of the systems and drilling rig. So there is a certain requirement for programmable and visual monitoring. Hence, the second generation drilling rigs are not only go deeper but also intelligent to some extent. By the early part of the century, there was an increase in demand from scientists and commercial entities for high data quality from subsea drilling operations rather than just increasing drilling depths. As such, new systems like CRD100 have been developed specifically for this purpose. The drill is designed to work in 3,000 meters water depths and continuously core to 65 meters below the seabed. The CRD100 system shown in the slide has deployed dimensions of 5.7 meters in height and 3.1 meters in width and length, making it suitable for shipping in 20s ISO standard high cube container. Once deployed, the drill can be guided to the work site as a seabed using altitude sensors, navigation sensors, a suite of cameras, and 4 thrusters with auto heading and cruise control functionalities. For tool handling, the CRD100 uses 2 arms, each with a 2-finger gripper designed to hold a wide range of tools, which include but are not limited to core barriers, rods to extend the reach of the bottom tool, also casings to protect the drill hole, and downhole scientific instruments which can be used to detect different grades of rock and minerals. Here's another successful commercial seafloor drilling rig from Canyon Offshore, the ROV drill system. It provides a seabed operating drilling module capable of carrying out a range of drilling, sampling, and in situ tests. It can recover samples to 50 meters below the seabed and carry out cone penetration testing, which is called CPD, to over 90 meters. Once deployed, the self-contained system can drill and test with complete real-time monitoring via cameras and subsea sensors. China also developed multifunctional seafloor drills that operating at water depths reaching up to 3,500 meters with real-time transmission capabilities. However, they are currently used primarily for scientific research purposes rather than commercial applications. Again, compared with second-generation drills, the third-generation drills now incorporate various in situ testing tools such as logging and CPD tools aimed at achieving multifunctionality while providing more precise geological information. It should be noticed that CPD technology plays a crucial role here. This is a cone with several sensors fixed in a pushing rod, while the cone penetrating into the strata sensors collect signals and transmit data to the logger in real time along depths. From those data, we can derive the soil properties quickly. So the application of CPD testing techniques on the subsea drilling rigs has addressed issues related to discontinuous sampling and sample disturbance while drilling, then promote the seafloor drill adaptability for marine engineering projects. Back to our topic, the latest seafloor drilling rigs can reach depths of over 200 meters. Take Germany and MBO Meepo 200 and China's Manatee #2 as example. The Meepo is remotely controlled from the research vessel. H-size drill tools for wireline coring drilling are stored on 2 magazines on the drill rig and allow drilling down to 200 meters below seafloor for coring soft sediments as well as hard rocks. A 2,500 long umbilical is used for lifting the ton to heavy device as well as for energy supply and data transfer. Average core recovery rates of close to 80% were achieved in different types of geologies, including hemipelagic mods, gas hydrate-bearing sediments, sands, glacial till, and carbonate rock. And the Manatee #2 is similar to it, but can reach greater depths. Recently, the Manatee #2 has achieved a record drilling depth of 231 meters, while maintaining pressure throughout the process. To the anthropology, and the Manatee #2 development is currently working upgrading seabed drill to reach deepest site in the ocean. Okay, now you may know the subsea drilling rig is, but you may not be clear about how its advantages deep sea mining. Here I would introduce engineering application example to use the SDF1 from Fugro, which is suitable for water depths of 4,000 meters, drilling depths up to 150 meters, which in situ testing function is typical third generation drilling rig. Here are some distinguished parameters. It comes with standard geotechnical samplers and have simple diameter of 73 millimeters. Fugro's inside testing tool is also available. The whole system contains of the rig, which the launch recovery system, passive heave compensator, and other systems. We can quickly compare the data quality of seabed drilling and offshore surface drilling in case study of this Gulf of Mexico, which shows that the subsea drilling has less disturbance, provide higher sample quality. And also there is a PCPT data graph. The last one, the contact resistance curve is very close to zero at the beginning. So this technology can accurately reflect the formation properties and identify any thin layers within it. Sure, when encountered with a hard strata, the drilling rig can collect samples which with simply resolved formations, proofs, challenging relevant soil properties can be derived from the CPT data. The integration of sampling and in situ testing on subsea drilling rigs significantly enhanced the reliability of data from deep sea exploration and engineering applications. Natural gas hydrate, which is the most potential clean energy source, is widely distributed in deep sea areas. The investigation sites of W118 and the recovered samples are shown that the that the safety data from formation above the hydrate is displayed in the right. From the original safety data, we derive the properties which give us insight into the geologic formations, which is essential for slope stability analysis and foundation design during the mining process. To sum it in brief, by analyzing samples and then CPT data, researchers can predict the characteristics of natural gas hydrate reservoir and evaluate the challenges in formation of stability during the extraction process, thereby laying a scientific foundation for the safe and efficient extraction of natural gas hydrates. In light of the discussion above, safe lower drilling techniques has many advantages and show great potentials for application in diverse industries. The second potential application is deep sea mining. The abundant solid mineral resource buried in the abyssal sediments, the deep sea drilling could help this process. Another application scenario is marine engineering, construction, engineering investigation apps to obtain the bearing capacity and other geotechnical characters and parameters of strata. The deep sea drilling could make it more efficient and lower cost. That's all I want to share here today. Thank you for listening. And our team is also preparing to develop an subsea drilling rig. We warmly welcome the guidance and discussions from experts and peers in the audience. Thanks a lot again.
Thank you, Professor, for the nice presentation. Is there any questions? Okay, if there is no question, we can move forward to the last presentation. Professor Márcio Almeida. The title of the presentation is Offshore Geotechnical Solutions from Advanced Physical Modeling to Applications. Thank you.
Okay. Let me see if I understand here. So, okay. Thanks for the invitation. It's a pleasure to be here and share with you some work I have done in the last almost 30 years in our lab. So the title of the presentation is Offshore Geotechnical Solutions from Centrifuge Modeling to Applications. And the LM2C lab is a multi-user centrifuge lab. It belongs to the Geotechnics lab which has almost 60 years. It's about as old as copy. But this is this lab has almost 30 years. So it started in 1996. The early studies involved, let me see if I, okay. The early studies involved transport of contaminants. But then late 2000, there was a big oil spill in La Guanabara Bay, and we were invited by Petrobras to analyze to perform studies of pipelines, movements of pipelines, and that triggered a series of subsequent studies. And the first thesis was finalized in 2005. And then we have been doing studies of offshore engineering involving renewable and non-renewable energy. And in 2012, we acquired a second centrifuge. That is a drum centrifuge, and that's a beam centrifuge. And that way, our scope was enlarged, so we could do a wide range of studies. And during this time, we have been doing, as I mentioned before, pipeline, then risers, that was with Technip, mud mats, submarine slopes. We did also performed with collaboration with Cambridge and University of Gustave Eiffel in France, embarked shaking table with seismic studies. These three in bold are the three projects we have nowadays underway. It involves debris flows, submarine debris flow, seafloor subsidence, torpedo anchors, which I'm going to talk with today, and also monopile foundations for the wind towers. These are the two topics. And I'm pleased to tell you that we are going to get a new project in early 2025 in carbon capture and storage, and the influence of that on slope stability. So that will be challenging. And so far, you have 28 studies. That actually is 20% of my overall number of students. I do, so this is, okay. Why to perform centrifuge modeling? Well, as the soil behavior is strongly dependent on stress conditions, so you have to, the 1G model, as you say, the stress involved are quite low. Hello? Yeah, thank you. So, as I was saying, the soil behavior is strongly dependent on stress conditions. So if you do a 1G model, the stress involved are quite low. So then you submit the principle of centrifuge modeling is to submit an n times smaller model to a NG acceleration. So you have inertial stresses that are close, are the same as in the prototype. Okay? So strains are also the same. And you have scaling laws that regulate force and velocity and all the rest, frequency and so on. So it's out of, I cannot talk to you about this. In China, there are quite a few centrifuges. In Brazil, we have two. In Brazil, we have three, two at Copy. The third one, 500 kilometers north of Rio at UF University. There's a fourth in Latin America. So let's go on. So torpedo anchors. You see here torpedo anchor to be deployed, resting on a vessel. And you have here the torpedo anchor is about 100 meters above seabed. So it released, and it goes at a certain depth, and the mooring line is then taken to the floater, to the floating vessel. Okay, well, that's basically how it works. So we have Petrobras is willing to enlarge the understanding of torpedo anchors. It's also called Brazil. In Brazil, it's mainly named torpedo piles, but it's actually an anchor. Internationally, it's more people use more torpedo anchor. But anyway, what can we enlarge this doing cluster studies, more than one torpedo at once, or the influence of inclination, all the rest? So this was done in physical modeling, and we have here we use acceleration 100 times, but the model actually we have a model 1 to 4 prototypes. So you have actually model a 6-meter torpedo, not a 23 meters. So how can you overcome that? By doing numerical modeling. So the numerical modeling is an important, very important complement, even if you do one-to-one. So it calibrates with very good quality data, the numerical models. Okay? We'll come back to that later on. So the first thing we do after our model is in flight, it's consolidated, and so on, is to measure the strength before the pull-out test, okay? So you have here, you measure with T-bar. The T-bar has been around for 30 years, developed at UWA, Australia, and it's being used offshore also. So these are the point resistance values. The point resistance is P upon A, but you have a NB factor, so that works. Then you may have an undrained strength that goes like that. So we have here 6 clay measurements, and the points are related to actual values measured offshore. Okay. So just pay attention to this length here. So you're going to have an average value, and use that average value later on. I'll show you. So that's a prismatic box. You can do in the same model or in the same clay bed 5 tests typically, and you can see here the torpedo piles, and here cross section here you may do either an isolator or single pile or a cluster, as you show here. Okay. This distance have been assessed, and they are okay with literature. It's actually not working so well, this thing, isn't it? It doesn't go all the time. But anyway, let's go. Let's carry on. So this plot shows normalized forces. How is normalization done? You divide the force by that average undrained strain value and the shaft area. You see? Shaft area. So you have a normalized force. And it's plotted against normalized displacement, again, the diameter of the shaft diameter, okay? So you see here that as you increase the inclination, the force increases. And that is being nicely put together here. You have also, the displacements also increase, right? As you incline. So you have force, not normalized force, but and normalized displacements plotted against pull-out inclination. So the angles, the inclination goes in direction, right? So both increase with pull-out inclination. That's the first interesting conclusion. But you've got to assess if our centrifuge modeling is doing right. So you have assessed that by comparing measured values with IPI predictions. So you have IPI predictions. It's interesting to see that it nicely underpredicts, as it's good for a design model, design procedure. Around 90% for the T120. 120 stands for tons, so it's 120 tons torpedo anchor. But another torpedo anchor is being assessed in physical modeling, numerical model, not yet used in situ, which is a T150. And I don't show the results here, but the underprediction is slightly smaller, 13%. So let's move. But I mentioned earlier on that there is an interest in doing cluster of torpedoes. So you have the torpedo, vertical torpedo anchors here too. You have that's the beauty of physical modeling, isn't it? You can do parametric studies. These are all in the same clay bed, but you can compare different clay beds also. They are always, all of them more or less close. So we have here, that's a single pile. So you see the torpedo, it provides much higher loads. 45 degrees, so similar results, isn't it? Force increases, again, normalized forces, and displacement also increases. So you have done three displacement, three space, 2.5, 3, and 3.5. Okay. Now we compare cluster, vertical cluster with single piles here. So you see 2.5, 3, and 3.5, and you do the same for inclined pull-up. So you have single anchor. That's the average of all those tests. So you see the 45 degrees provides a higher value, and also inclined. So you see that both for vertical and 45 degrees, the optimized spacing is 3 times the full diameter. I'm talking about times dt. dt, if I come back, dt is 3 times that overall diameter with fins. Okay? So, let's go. Numerical studies are underway with LaSalle, by the way. And so partial conclusions, torpedo anchors. Without force of isolated piles, experimental results are close to APIs. That's good news. Normalize the displacement, peak force decrease with the inclination of the force for both isolated and clustered piles. In piles in clusters, space D, 3 times the overall diameter, including fins, provide the highest efficiency, and have got the good news that our paper has been accepted in ocean engineering. So, okay, now we move to a second topic, which is monopiles, foundation modeling. And there is a lot of interest in Brazil of using monopiles. Piles, by the way, is 80% of the wind offshore wind towers foundations are in monopiles. So that's a lot of interest of studying this. But these structures are slender to cyclic due to environmental wave, wind, and so on. And the second main, let's say, loading or interest is vibration. So we've got to assess the vibration of the towers so that these towers, they oscillate due to this, the loading. And these you have a plot of frequency versus acceleration, we can say is similar to acceleration. And it normalized, and you can see that you've got to either put in this range, or in this range, or in this range. So this is a balanced design. So this is too costly. This is not so worse, let's say. So, most designs are done in this range. So you got to have to test to assess the frequency, natural frequency of the tower. But before we performed monotonic studies, this is we took part in the international benchmark with 7 other groups from all over the world, Europe, and we plot these 2 centrifuges. They are similar size, in 107 acceleration, the other 96 hours. So they plot together. When they normalize, they plot like this. But this graph is here. Our study this here is there. Okay. So the 8 groups are here. So we are okay. Despite you see being below here, isn't it? You are here, but it's okay. But that's not a problem at all. So it's in 1 minute. So let me rush. So we've done a numerical comparison that was shear modulus and damping, Moculum modeling, and this is these are interesting work done with Lassell, and you have comparison here. Numerical model, blue, and the 2 physical models, red, green. So a good comparison. Monotonic test, that's a very important issue. I'm going to pass that quickly, just saying that ejected piles are piles. Most of PI curves are done for slender piles. Monopiles are medium stiff. So the API doesn't work well. So you can see here, API here, and physical modeling, and the proposal, more recent proposal by Klinkvoort, they compare well. So we have done long-term cyclic behavior. A very good story, just a paper being submitted. So we've done 10 to the 5 cycles. The lifespan is 10 to the 7. So that's unique. There is nobody else has done that before. So we have measured stiffness. You see this stiffness here, and here, I suppose yeah. So this is stiffness. The stiffness goes like that. So K1, Kn to K1, it varies like this. So in a logarithmic fashion, let's say. That's an interesting result as well. So also, we've got to analyze that's the natural frequency without soil. And that's with soil, both at 100 G. So it's important, the soil structure interaction. Very important to take that into account. And as you cycle, to the 5, the natural frequency increasing time. High. And that is very important for design, as I mentioned earlier on. Okay? So let's now to partial conclusions. Monotonic test, overall good agreement with benchmark studies. PI curves show the need to adjustments regarding international standards. Cyclic test, second cycles according to a logarithmic function. Soil structure interaction has a large effect on natural frequency, and the natural frequency of the system is increasing with increasing number of cycles. Overall, final conclusion. Centrifuge test. That's just physical model, just a part of the overall analysis. This is by it's a very important concept here. So we have a conceptual model, we have a rigorous model. I used for design, but actually, because of its quality, it used to calibrate. I see. Okay. Okay. But the last slide, sorry. Well, okay, so the main importance of physical modeling is validating numerical and conceptual models, as I mentioned. The numerical or even the conceptual model are using the direct design, not physical modeling. You see here field tests. How can you do a full-size field test in a monopile? Impossible. I do embankments on soft clays. Structure is quite low, but not in offshore environment. It's quite challenging and difficult. So that shows the great importance of physical modeling in offshore industry. Okay. Now I close showing my group. Part of my group, we are about 30 people, lecturers, postdocs, master and PhD students and technicians and undergraduate students. So I would like to invite you to visit our lab. It's in another building, not in the main copy building, but just tell me if you are interested and can arrange that. Thank you very much.
Thank you, Professor Márcio. Any questions? One question.
Thank you very much, Professor, for your presentation. So I have a general question, maybe not so relevant to your presentation today. So because, you know, there is a concept called the shared mooring for the floating offshore wind turbine. And I don't know if you know this, but basically speaking, there is an anchor.
Yeah, I know. Yeah. I have a former student.
Yeah.
It's to Gustave Eiffel. He's working with share anchors.
So I know very little about the geotechnique. I'm not the geotechnical guy. So my problem is we basically think about imagine that there is an anchor and connecting two mooring line. The two mooring line from different direction. They always have the cyclic, from the mountain point of view, they have the cyclic loading. And do you think, first question is feasible to do this for this shared anchor? And the second question is, do you think, in your opinion, what type of anchor we're gonna use for this kind of design? And from a mountain point of view, any liquefaction that could be harmful to the bearing capacity of the anchor?
Yeah.
All right. Thank you very much.
A very large question, let's say. Yeah, I'm saying that this student of mine, he's got a Marie Curie fellowship at Gustave Eiffel. He's actually doing exactly what you're mentioning at the Gustave Eiffel University nowadays. Present share anchors, suction piles. You know, they are not using let's say torpedo anchors because they don't have the tradition over there in France. But you know, but it's quite challenging, isn't it? Because they have multi interaction because one floating vessel pulls out to one direction, the other pulls out. So we've got to combine those. There are a number of combinations, but it's very important and it's a hot topic at present.
You think that suction pile could be one of the best options for the shared anchor?
I think so, yes. Again, in
But we are
Brazil, we don't
talking
have, I suppose in Brazil don't use so much suction piles, but yes, I suppose it is in Brazil we have carbonate soils, isn't it? Even, I should say that even monopiles may not be a best solution. So gravity platforms, even jacked piles may be a better solution when you are talking about carbonate soils.
Okay, thank you so much.
Thank you.
Okay, we've reached to the end of the presentations, and I would like to invite Professor Seijane and Professor Duan for the closing, please.
Okay, we sit down. You start?
I start?
Yeah.
Anybody can hear me? It's a full day presentations, and I think it's a very good exchange between our two universities, and especially we have invited Mr. Hu from the Sinlook International to join us. And it's a very great support to the presentation. And the president of the Sinlook International will have a very special banquet on Monday night. He's also the co-chair together with Seijane for this workshop. And we do trust this full-day presentations would be the basis for the future collaborations, especially for our joint application to the projects granted from the 1% policy. I do trust. And like the last presentation, the Tsinghua University will be very interested in how to build a scientific setup by other ways rather than by the centrifugal setups. And it's not easy to take a big scaled modeling by this setup. So we're trying to find the other way. And we will find some other time for a discussion about how we can work together. It's a lot of money for the scientific setup. But anyway, it's a very I think it's an fundamental research for such a setup. Tsinghua has been working on that for I think for 6 years, and we have specific solutions for the setup. And Professor Wang Fangcheng, he brings some new solutions for that setup. But this workshop, we don't have enough time for discussion about that. We will have a specific discussion on that. So I think this workshop has been very successful for our preliminary design for the basis for the application of the future projects, especially this year or the year after. Okay, so I would like to, on behalf of the China side, I would like to thank Sijin, thank all my friends, the colleagues in Copy, from Copy, and the professors, the older ones like Liu Shu, Roman, Sphere. They are not here this time. We will seek for their advices on our future collaboration. And CINUC will take a lot of steps on on how to fasten our collaboration or have a close collaboration. And the vice president of the CINUC Research Institute is coming the day after tomorrow. Am I right, Shifeng? Yeah, and he will also have some new considerations for how to keep our collaboration, how to fasten our collaboration and make the collaborations more successful, and we will have more fruitful results for the future. So thank you very much. Thank you, especially.
Just a few words. First of all, to thank all the delegation from Tsinghua, Shenzhen. So Mainland Duan, it's our old friend for long cooperation, and I think we are in a new continuation, a new track for this progressing this collaboration. It's very important to have here today Mr. Wu from CINUC Brazil. It's our partner in this cooperation. CINUC Brazil is getting bigger in Brazil. It's very important that we have a strong and solid cooperation. I think we had the flavor of the research work in progress here in Copy and also in Tsinghua, Shenzhen. I think it's an opportunity to meet each other and plan possible joint projects that we can propose in coming years. In relation to my field, special field, I'm now responsible for the implementation of a National Research Institute on Ocean Research. It's important also to be in contact with not only with your university, but also with people from oceanography in China, as we did in 2 months ago. And I think we can increase the cooperation, Brazil, China, and with the visit of the Chinese president in the end of the year for G20. This year, Brazil is in the presidency of G20, and we have a group we call Oceans 20 that are trying to put the ocean on the top of the agenda for the G20. We need the help from Professor Duan in this sense. We would like very much to have the Chinese representation on this initiative also. And then I thank you very much for all the attention. Professor Murilo, that helped me a lot. Professor Milad and Gero Group that organized the event. Professor Sujian that has been with us for a long time in this cooperation, and others that are coming, like Professor Márcio, Jandavi, and others. I would like to ask you to come here for a photo inside and another photo outside. Thank you very much.
Thank you.